Hello all, and welcome to this continuation on our lecture series for Biophysics for Health Science majors in the Post-Bachelor scene. In this lesson will cover electrical circuits, typically talked about in a physics course, and we'll get a little bit into the cardiovascular and nervous systems on how we can compare those to electrical circuits in physics. For these types of circuits, we're talking about direct current or DC circuits specifically. Typical parameters that we'll see are the voltage or the battery supply. That would be the electromotive force or the driving force in a circuit. The reason why it's not a force per se is because it's not in units of newtons, but it's the action that encourages electrical flow in a circuit. We will also have resistance, which has to do with the component resistors. In a circuit, it is a measure of the difficulty for an electrical current to flow, and the units for that would be in ohms, and usually will represent with the symbol R. Going back to voltage, the units would be volts, and would usually be represented by the symbol V or EMF for electromotive force. Conductance is something that is not usually talked about in a physics course, but usually shows up more when it comes to biophysics. It's actually just the inverse of resistance. Conductance, which we'll see in the conductor components, or which are seen in conductors in circuits, they're a measure of the ease for an electrical current to flow, and because they are in units of Siemens, but usually represented by a G symbol if we're writing them on a circuit. Because a Siemens is actually just 1 over an ohm, another term to call these are mhos, M-H-O-S, the inverse of ohms. So essentially, if you ever have a system where you have resistance, you can just take the reciprocal and you automatically have the conductance. Though resistance we'll talk about for physics circuits. Conductance is more for actual biosystems. Lastly, we also have current, which is the flow of charged particles. Units are represented with the symbol amps, or with the units amps. And I should make one change the symbol. Let's see. The symbol is usually used with an I to represent current flow. Let's see. So a way of representing all these is the most basic of a DC circuit, which is some voltage with current flowing through it, going through at least one resistor. Now, a way of representing circuit notation for our battery supply or our power supply, we usually represent that with a few bracketed lines, some smaller ones and larger ones. This represents our main power supply causing the main voltage in our circuit. Any of these jagged lines will usually be resistors, though since resistance is the inverse of conductance, sometimes the same symbol is used for a conductor. You would just see a different label for the value above it though. And then any straight lines, we just consider that a wire, and we usually consider the resistance of a wire to be around effectively negligible. Conventional current flow is where we look at current as flowing in the direction of a positive charge, leaving our voltage, power supply, and traveling in the circuit toward the negative terminal of our power supply. That conventional current flow is how we direct a lot of our calculations. In reality, the actual charge character in a circuit is an electron, a negative particle. So real current flow is where we treat current as going from the negative end to the positive end. Now, in reality, there aren't electrons necessarily moving once we get into alternating current flow, but that would be beyond the course of this class. For most of our calculations, we're just going to be looking at DC current flow in the conventional end, leaving the positive terminal and entering the negative terminal. or wherever a positive particle would leave and enter our power supply. Ohm's law is the primary one that we have for any component in a circuit, where we have the voltage at that point is equal to the current flowing through that point multiplied by the resistance to flow through that point. Therefore, a volt is equal to an amp ohm, or if we use the inverse of resistance for conductance, a volt is equal to an amp per Siemens. One simple circuit resistor. We might be given two different components. Usually we know the power supply in our circuit, and usually we know the resistance of all of our resistors. So hypothetically, if we had some 10-volt power supply powering current through a 5-ohm resistor, what would be the current? Well, if volts equals IR, then rearranging to solve for I would be voltage divided by resistance. 10 volts divided by 5 ohms would be 2 amps. And for drawing in the current, we'll treat the longer end as the positive terminal and the shorter end bracket as the negative terminal. And so we'll have current flowing like such. Now, there are two simple ways to represent current flowing through a circuit with more than one resistor, which have biological significance. One way is representing a circuit that has resistors in series, essentially multiple resistors that are on one single path, where all of the current that is flowing through that circuit flows through resistor 1 and also flows through the later resistors. Things to note is that the voltage drop across those different resistors in series will vary. Some of the main power supply, of the starting power supply, some of that voltage will be lost across one of the resistors in a series, and then some of the voltage will be lost across another resistor. But one thing to note is for resistors in a series path, the current that flows through that path is constant and is the same value that flows through both resistors or any resistors along a series. The key for any kind of complex circuit is to simplify it to its equivalent circuit, which is simplifying all those resistors to just one resistor. Well, let's say we have one 25-volt power supply circuit that has two resistors, resistor 1 that has 7 ohms of resistance, and resistor 2 that has 3 ohms of resistance. We will have to simplify them to some equivalent total resistor in order to determine what is the current flowing through the system, which we'll eventually figure out is 2.5 amps. Now, the trick here is that for resistors in series, to simplify a series path of resistors, simply add the resistance of every resistor along that path. For example, resistor 1 and 2 are along one single path, they are in series. So the equivalent resistance for the series resistor would just be all those adding together. 7 plus 3 ohms, which equals 10 ohms. And because doing so now brings us down to one single resistor, we'll just call that the equivalent total resistance. Now, the total current, which is going to be represented through our single resistor simplified path, will just be the power supply divided by the total resistance, or the simplified resistance. Therefore, 25 volts divided by 10 ohms is 2.5 amps. And this is the current flowing through this equivalent resistor. Therefore, any resistor that this was simplified to that were on a series path, that same amount of current will be flowing through those resistors in that series as well. In other words, we have 2.5 amps going through this path. This path is just the same as going through this single path right here. So we can say that there are actually 2.5 amps flowing through resistor 1 as well as resistor 2, because they were a series path that was simplified into one. Therefore, if we know that 2.5 amps are going through resistor 1 and 2, we can determine how much of our original power supply gets dropped around the first resistor and the second resistor simply by our total current being equivalent to I1 and I2 flowing through resistor 1 and resistor 2. Voltage 1, the voltage that gets dropped across resistor 1, would be its current flowing through it times the resistance. So 2.5 amps times 7 ohms, or 17.5 volts. And then resistor 2, its voltage drop would be 2.5 amps times 3 ohms, or 7.5 volts. Something we should note is that for a series path, we should have all the voltages across each resistor add up to our main power supply. So the 25 starting volts of electrical pressure, we're going to lose 17.5 volts of pressure across resistor 1, and then the remaining pressure across the final resistor. That's another way to check to make sure that our math was done correctly. Now, another path that may be looked at is having resistors in parallel. Essentially, let's say we have some branch point in our circuit where we end up having multiple paths that each have at least one resistor on each path, and then all those branches come back together at some point. These 2 points are called nodes, or points of branching. Between 2 nodes, the voltage drop across the entire path will be the same across each parallel path. So if we only have one resistor on each path, the voltage drop across this entire path or this single resistor will be the same voltage drop across here and here and here. If we had multiple resistors on a single path, then the total voltage drop would be the same, but some of that would be lost across one resistor and then another if they were on the same path. Sort of like if they were in series. Now, current, however, is what splits up as we have parallel paths. So let's say we only know initially our starting power supply, and we only know the resistance for each resistor in our circuit. What we're going to need to determine is the amperage that is flowing through our current, and what's the amperage that flows across each individual circuit. Well, this will initially be easy in the sense that resistor 1, 2, 3, and 4, they all exist on 4 separate parallel paths. And here's how we simplify those parallel paths. What we have is resistor 1, 2, 3, and 4 are all on parallel circuit paths, and they are 4, 8, 6, and 12 ohms respectively. When it comes to paths that are in parallel, as long as each parallel path only has a single resistor, then we can use this formula, where the equivalent parallel resistance of simplifying all those parallel paths into a single path resistor is just the sum of all the reciprocal resistances and then all raised to -1. Therefore, that would be 1 over 4 plus 1 over 8 plus 1 6 plus 1 12, which is 25 24ths inverse ohms. Raise that to -1. We have an equivalent circuit of our parallel paths simplified to 24 over 25 ohms. And because this now gives us a circuit that has only a single resistor, we'll just call that RT. So to find the current flowing through this compressed path right here, that will just be 24 ohms divided by 24 over 20, or 24 volts divided by 24 25ths ohms. which just becomes 25 amps of current. Now then, what we have here is the current flowing through this compressed circuit. Because this compressed or this simplified component was from parallel paths, some of that 25 amps is going to be flowing through part 1, some will be flowing through path 2, path 3, and some of the current will be flowing through path 4. And here's how we determine that information. We already have the total current as 25 amps. That's good to know. That tells us for all the current that flows through each of these individual paths, if our calculations are done correctly, those currents should add up to the main current. Because as 25 amps breaks apart into different paths, it will all come back together and flow as 25 amps once all those branch points come back together at that node. Here's the trick we're going to use. The total voltage drop across a path will be equivalent for each parallel path. Now, between this point and this point, we are going to have the full 24 volts drop. That's because we do not have any more resistors after this node or before this node. So the entire 24 volts has to drop across these two nodes, which means each path has a voltage drop of 24 volts. And since each path only has one resistor, that 24 volt drop occurs at each resistor. Therefore, our parallel voltage for each path is 24 volts. Current flowing through resistor 1 will be those 24 volts, dropping out resistor 1, divided by its resistance of 4 ohms, or 6 amps. For resistor 2, the current that flows through resistor 2, or this path, will be those 24 volt drop divided by 8 ohms, or 3 amps. The current flowing through path 3 is going to be 24 volts divided by 6 ohms, or 4 amps. And through path 4, that will be the 24 volt drop divided by 2 ohms, which gives us 12 amps flowing through this path. So path 1 has 6 amps flowing through it, path 2 has 3, path 4 would have 4, or path 3 would have 4 amps, and path 4 would have 12 amps. And if we add up all those currents together, 6 plus 3 plus 4 plus 12, that adds up to 25. So we have 25 amps of current as we're approaching this node, and we end up having 25 again as we meet up at the next node. Now, those are two straight examples where we just had things in series or we just had things in parallel. Realistically, what if we had a more complex circuit, also called a complex RC or a complex resistor circuit? Let's look at this sample problem. A circuit composed of 5 resistors was prepared as shown above. Determine the following sets of information. Determine the current flowing through R1 and R2, i.e. what's the current flowing through, what's current 1, 2, because whatever current we determine that flows through this path, it'll be flowing through both resistors evenly. The same current that flows through resistor 1 will flow through resistor 2. We'll have a current that is the same flowing through resistor 3 and 4 because they are on a series path. We will also determine the current flowing through resistor 5, which is simply going to be whatever starting current we have. Some of it will go through path 1, some will go through path 2. That current will meet up and we'll have the total current again, all flowing through resistor 5. Then we'll also determine the voltage drop across each individual resistor. The voltage drop across the total of R1 and R2 will equal the voltage drop across the total of R3 and R4, and the voltage drop across any of these paths plus the voltage drop across R5 will end up being our total voltage. Now, a trick that was not talked about, because usually this does not happen in most cases. how would we simplify a power supply? Well, if you have power supplies in series, just add up their total together. And since through convention, parallel paths must have the same voltage, essentially we have two 6-volt batteries along one path, we have two 6-volt batteries along another. 6 plus 6 is 12. We have 12 along one path, 12 along the other. That's the same as if we just had one single 12-volt battery. In other words, if you have parallel paths for batteries, we just need each path to add up to the same value, and then pretend we only have a single one of those. The reason being, if we had, say, a 6-volt, if we had 6 volts, if we had 12 total volts along one path and 10 total volts along the other, that higher voltage would try overcharging the lower voltage path and could essentially cause catastrophic breakdown for overcharging a power supply beyond what it's meant to hold. All that's meant to say is we have one path that had two 6-volt batteries, they add up to 12. We had one path that had two 6-volt batteries, they add up to 12. Two parallel paths that have 12 volts is just the same as having a single path that has 12 volts. That's why we have a power supply that adds up to 12. Now, for our main circuit, let's start simplifying, and it's best to simplify things that are either just in series or just in parallel. For example, we have resistor 1 and 2 that are just in series, and we have resistor 3 and 4 that are just in series. And we can simplify them like such. Resistor 1, 2, which is just the equivalent resistor of 1 and 2. Since they're in series, we just add up resistance 1 and 2. 1/2 ohm plus 1/2 ohm, which equals 1 total ohm. And resistor 3 and 4, we can simplify those to a single equivalent resistance because they're in series. 3/4 plus 5/4 ohms equals 2 ohms. We haven't done anything with resistor 5 yet, so it's still 10/3 ohms. Now, we have two parallel paths that each have a single resistor on it. We can now simplify these two paths into a single equivalent parallel resistance. Therefore, RP, or that parallel path simplified into a single path, would be the summation of resistance 1, 2, 3, and 4, which we're just going to take the inverse reciprocal, or the reciprocal of resistor 1, 2, and resistance 3, 4, and then raise them to the power of -1. We end up having 1/1 plus 1/2 inverse ohms, which becomes 3/2 inverse ohms, which inverting that becomes 2/3 ohms. And that would be simplifying resistance 1, 2, 3, and 4 into one single equivalent resistor, as if we replaced all four of them with a single resistor. And now this parallel simplified resistance is in series with resistor 5. So to simplify that one, we now have our total resistance, or our total equivalent resistance of R1, 2, 3, 4 plus R5, because they're both in series, and they all add up to 4 ohms. Now then, to determine the total current flowing through our system, i.e. the current that has to be leaving our power supply and entering our power supply by the end, that will be our total equivalent battery supply, which we determined was 12 volts, divided by our total equivalent resistance, which is 4 ohms, or 3 amps. So we know that 3 amps is flowing through any particular single path. So to start solving for this equation, let's start going backwards now. The first step going backwards is we had our parallel resistor, and we had our simplified parallel resistor, and we had resistor 5. They were all along one single path, which if we had 3 amps leaving here, then we know that 3 amps is flowing through our parallel path simplified resistor, and 3 amps is flowing through R5. This will be helpful in determining what's the voltage drop across each parallel path in our resistance. So the parallel voltage is going to be equal to the current flowing through 1, 2, 3, 4 times our parallel path resistance. The current flowing through resistor 1, 2, 3, 4, or RP, is going to be those 3 amps times 2/3 ohms, or 2 volts. Now current 5, that's just going to be 3 amps, because since this is one single path, 3 amps will have to go through each resistor that is just along this single path. So we already know what I5 equals, which means we can calculate V5, or the voltage drop across resistor 5, which should be its current flow times its resistance, or 3 amps times 10/3 ohms, or 10 volts. Now, let's take those 2 volts for our parallel paths and apply them. Going one step further, essentially what we have is 2 parallel paths that each have one equivalent resistor. We have R12 and R34. Now, the voltage drop across this entire path must be equal to the voltage drop across this entire path. Because we determined that the voltage drop across RP is 2 volts, that means that there's 2 volts being dropped across here and 2 volts being dropped across here. So the current flowing through resistor R1 will just be that 2 volts divided by 1 ohm of equivalent resistance, which gives us 2 amps. And then I34 is going to be the current flowing through path 3-4, which ends up being 1 amp. What this says is, as we have 3 amps flowing from our power supply, 2 amps are going to flow through all of path 1. And 1 amp is going to be flowing through all of path 2. Then they meet up, and we have our 3 amps going again through R5. Here's what's nice. Path 1 and 2, they were really just a couple of series resistors. And we just determined that through all of path 1, we have 2 amps flowing. Because these 2 resistors are on series, 2 amps is flowing through R1 and flowing through resistor 2. Similarly, 1 amp is going to be flowing through all series resistors along this bottom path. Therefore, we now have all the information we need to solve the remainder of our problem. The voltage that gets dropped along resistor 1 would be its current flow 2 amps times 1/2 ohm, or 1 volt. Similarly, because the current and resistance are the same for R2, by happenstance, that will also be 1 volt. In total, we have 2 volts being dropped across path 1. Now then, across path 2, we should have everything add up to 2 as well. What we have is at V3, or the voltage drop at resistor 3, would be 1 amp times 3/4 ohms, or 0.75 volts. And then at resistor 4, 1 amp of flow divided by, or times 5/4 ohms would be 1.25 volts. Path 3 and 4, which are in series, add up to 2 volts as well. So, in summation, what we have here is simplify our complex battery supply to a single 12-volt battery. What we have is 3 amps leaving our circuit, 2 amps going through our first parallel path, 1 amp flowing through our bottom parallel path, a total voltage drop across each parallel path being 2 volts, specifically 1 volt across both R1 and R2, and then 0.75 and 1.25 across 3 and 4 respectively. This is the same as if we had a single path that lost 2 volts, which means of our 12 volts, we lost 2, and our calculations check out because the remaining 10 volts gets dropped across resistor 5, which respectively have 3 amps flowing through it. And that is just a complex resistor circuit. Another component in physics that shows up in biological systems are capacitors. And capacitors, they have a property called capacitance, which is measured in units of farads. More realistically, in real life, we would see millifarads or nanofarads. However, just to keep math simple, we'll talk about farads. They're represented with the symbol C. Their power is the ability to either store and hold charge or to keep charge separate, to keep positive and negative charges separate from each other. And in physical circuits, or in circuits like with electrical work, they're meant to hold charge and then disperse it. Here what we have is what's called a parallel plate capacitor, where essentially we have one side trying to store a bunch of positive charge, trying to keep separate from another plate that's storing a bunch of negative charge. And what we see here is just electric field lines. This is meant to help show that parallel plate capacitors are very good at separating charge. Now, they are the more surface area of the plates, the greater their capacitance. The further the distance of the plates, the lower the capacitance, or effectively their ability to separate charge. Looking at RC circuits, this is actually what happens when we have the combination of a resistor and a capacitor, or multiple of each. And what we care about for those types of circuits is what are called the time constant tau, which is simply the simplified overall resistance multiplied by the simplified overall capacitance, which says that 1 ohm times 1 farad equals 1 second. So this time constant is in units of time. What we're going to see as we have capacitors, we could have capacitors in series and parallel, and our main equation we're not going to evaluate, but we're going to interpret is capacitance for a capacitor is equal to eta A over D. Eta is just the dielectric constant, 8.854 times 10 to the 12th farads per meter. The two parameters that we can actually alter is the area of a capacitor in meters squared and the distance of separation between plates in meters. It's because of this equation that if we were to increase the area to have larger parallel plate capacitors, their ability to separate charge increases. But if we further the distance between them, then their ability to separate charge decreases. Well, let's look at a situation like this. Typically what we have for when it comes to RC circuits, we have what's called a switch that can connect one path initially and then can connect another path afterwards. Initially as we're charging a capacitor and then connect another path to release that charge. Though we're not going to get too hard into these equations, VB, or the power supply across the battery supply, is going to be equal to the voltage dropped across our equivalent resistor plus the voltage difference across our capacitor, which just means that in these cases, overall, once we are charging our capacitor, or once we have our capacitor connected to our power supply, whether charging or discharging, the battery supply voltage difference will equal the sum of the current times the resistance plus charge Q over capacitance of our equivalent capacitor. That's more for introductory information. Some other introductory information could be that as voltage varies with time, it equals IR plus Q over C. Another way to show that equation, if we're charging a capacitor, letting it build up charge, then that would be equal to the battery supply times E raised to T divided by tau. T being how long we've been allowing our capacitor to charge, plus our battery supply times the quantity of 1 minus E raised to negative T over tau. The first half being the resistor power supply, the second half being the current battery supply. Let's see. Good. And because tau is just the equivalent resistor times capacitance, we can replace tau with RC. Now, if we were discharging a capacitor, specifically, well then the current voltage across that capacitor will be the initial voltage we charge it to. And then once we start allowing it to discharge, times E raised to negative T over tau, or E raised to negative T over RC. Something interesting is that component in our equation, 1 minus E raised to negative T over RC, we can think of that as what percentage of the maximum we can charge our capacitor has it been charged to. And after 1 RC seconds, if we replace time t with 1 RC, RC over RC just drops to 1, so 1 minus e to the negative first. That's approximately 0.63, or we have charged our capacitor to 63% of the battery supply. After twice the time constant, we're at about 86%. 3 times the time constant, we're about 95% of the way charged compared to our power supply. At 4 RC, we're about 98%, and at 5 RC, we're at 99%. Typically, at around 5 RC seconds, after that amount of time, it's usually assumed that we have charged our capacitor, VC, to be equal to the battery supply's voltage, VB. Now, that's all introductory information. Let's look at some samples of simplifying circuits. Let's say we had one RC circuit with a single resistor and 3 capacitors that are in series, C1, C2, and C3. 1 capacitor, 2 capacitors, 3 capacitors. To simplify all these to one equivalent series capacitor, think of it as the opposite of resistance. For series capacitors, we are going to sum all of their reciprocal capacitances and then raise them to -1. So in this case, our series capacitance would be 1 over C1 plus 1 over C2 plus 1 over C3, added together and then raised to -1. That's because this is equivalent to having a single capacitor with the parallel plates further apart from each other. If we have parallel plate capacitors, well, to simplify those to a single resistor, it's the same formula as if we had resistors in series. For capacitors in parallel, simply add up the capacitance of each capacitor that is in parallel with each other. Well, what this does is it's similar to having one single capacitor that has a substantially larger area, thus allowing it to separate more charge. So our main equations are going to be the voltage across our capacitor with time will be, if we're charging it, it will be our power supply, our battery, multiplied by the term 1 minus e raised to negative t over tau. If we have parallel capacitors, just add up their capacitance to simplify them. If we have series capacitors, sum the reciprocals and then invert. As far as determining what percentage a capacitor has been charged, well, that would be negative tau times the natural log function of 1 minus a. And that will equal the amount of time that has passed. If we were asked to see how long it would take to charge our capacitor to 50%, we would just put in 0.5 for a. When it comes to discharging a capacitor, the current voltage difference across that capacitor will be however much we charged it to, whether we charged it to the full battery supply or we charged it to half of it, whatever we charged it to, we will multiply that term by e to negative t over tau. And then, as always, our time constant tau is just our equivalent resistance multiplied by our equivalent capacitance. So, as far as typical problems that you might see if you ever take a standardized exam on this material, whether for accreditation or for entrance into a graduate program, here are some basic problems you might see. Let's look at the following circuit. We have a 15-volt battery supply with two resistors that are both in series. And along that path, we have two parallel capacitors, and then those paths meet up, and then we have another parallel path, or we have another path. We have another third capacitor. Now, this is a simplified circuit. In reality, we would have like some switch allowing for the current to flow eventually back to our circuit. Here, current would not be able to flow through these resistors as shown, but we're going to leave out the switch path just to simplify what we're looking at. Here are some basic equations. One is simplifying an RC circuit to a single equivalent resistor and capacitor. Afterwards, we can multiply those two to determine the time constant. After which we can solve more equations, which include what amount of time is needed for the equivalent capacitor to become 75% charged. And after 3 seconds, what would be the voltage across the charging capacitor? And once fully charged, i.e. if we charged it to the full 15 volts, after 60 seconds of discharge, what voltage difference would be across the capacitor? Well, when it comes to simplifying our resistor, our two resistors we had were in series, so let's just add up their values to a single equivalent resistor of 75 ohms. For our capacitors, we have the first two that are in parallel. Each path only has one capacitor, therefore we can just simplify these into one single equivalent capacitor by adding up their capacitances. 3 farads plus 9 farads equals 12. Now then, we simplified this to a single 12 farad capacitor, which that simplified capacitor, CP, is now in series with C3, which means to simplify them into one, we would add up their reciprocals. So 1 over CP, or 1 over C12, plus 1 over C3. That eventually becomes 2 inverse farads, which if we invert that, that becomes 1/2 or 0.5 farads. And because we now have a single capacitor, we'll call that CT. Well, drawing it is what we were asked to do in part 1. So we have our 15-volt battery supply, our equivalent resistor RT of 75 ohms and our equivalent capacitor of half a farad. Because we have these two values now, we can also solve part 2, which is simply taking RT times CT, 75 ohms times half a farad, which is 37.5 seconds for our time constant. Now then, the next part. What if we were asked to charge our capacitor to 75%? Well, we would use the formula negative t natural log of 1 minus a, plug in our time constant times negative 1, so that would be negative 37.5 seconds, times it by the natural log of 1 minus our percentage in decimal form, and that gives us 52 seconds. Or if our equivalent capacitor can store it, it will take 52 seconds to reach 75% of the battery supply's voltage difference. Now then, for part 4, what if we're asked the voltage after the capacitor has been allowed to charge for 3 seconds? Well, with that we'll use our equation Vc of t, or the capacitor voltage difference with respect to time is going to be equal to what is charging it, our power supply voltage, multiplied by 1 minus e raised to t over tau. That Euler number. Well, since we're using 3 seconds, let's just take our power supply of 15 volts times 1 minus e raised to negative 3 seconds over 37.5 seconds, which roughly gets to 1.15 volts. So after 3 seconds of connecting our power supply to our RC circuit, that equivalent capacitor will be risen to 1.15 volts. Now let's say we allowed our capacitor to run for a significantly long amount of time. We allowed it to charge effectively all the way to the voltage supply of our battery. After fully charging the capacitor, it was allowed to discharge for 60 seconds. Fully charged just means that our initial voltage difference once we start discharging equals our battery supply. If it wasn't fully charged, then it would be whatever we allowed it to charge to. And therefore, this would be the voltage across the capacitor. The answer will be the voltage difference that still remains on the capacitor. So Vc of 60 seconds of discharging equals Vo raised to e to the negative t over tau. Because we allowed the capacitor to initially charge all the way to the battery supply, Vo is just Vb, or 15 volts, and then we'll times that by e raised to negative 60 seconds over 37.5. And this essentially gets us to 3.03 volts. In other words, if we take our percentage factor, that just says that after 60 seconds, we have discharged the capacitor 80% of the way, and that about 20% still remains on the capacitor. So, groovy. Now then, we just talked about circuits like what an electrician might work with, or an electrical engineer. Let's start bringing this into the biological sphere. One thing we can do is talk about the cardiovascular or circulatory system, where we have current or blood flow going through our blood vessels. One law that affects certain parameters in our circulatory system is the Laplace law, which is that mechanical stress experienced, or the surface tension experienced by the walls of blood vessels, is directly proportional to the pressure and vessel radius. If there's a certain pressure inside a blood vessel keeping the walls from collapsing in on themselves, and they have a certain diameter, which is twice the radius, the tension of those walls is going to be equal to the radius times the pressure. Well, when it comes to surface tension in blood vessels, we'll look at pressure in kilopascals. A kilopascal is 1,000 pascals, and a pascal is simply a newton of force divided by a square meter of area. The radius will be in meters. Tension is going to be in newtons per meter, or force applied across some one-dimensional length. We can determine the tension in various blood vessels. For example, the aorta, which on average has a radius of about 0.012 meters and a pressure of 13 kilopascals. We could do the same for arteries, capillaries, veins, and the vena cava. And if we do such, what we end up getting is for the aorta, the tension, which would be the radius times pressure. As long as we convert everything to meters and pascals, that gets us 0.012 meters times 13,000 pascals. Or 156 newtons per meter of tension. For the artery, we're going to have 0.005 meters for the radius times 12,000 pascals, or 12 kilopascals multiplied by 1,000. And that would give us 60 newtons per meter. For the capillaries, well, that's going to be around 0.024 newton per meter. For the vein, the tension can be on average around 10 newtons per meter. And for the vena cava, they can get around 19.5 newtons per meter. The main trick of this was just, if you're given certain values, be comfortable converting them in order to have useful measurements. For example, if we're given kilopascals of pressure, when we're trying to figure out tension, you can convert it to pascals, and then we'll have the typical unit newton per meter. If you did not, then our units would be in kilonewtons. Per meter. So let's keep everything in newtons per meter. Tension is just radius times pressure. Now then, properties of blood. This acts as a non-Newtonian fluid. Blood as a non-Newtonian fluid. Typically, the viscosity is a function of shear rate. In Newtonian fluids, viscosity is a constant during changing shear rate. Shear rate is the rate which layers within a fluid, called laminae, move past each other. Similar to taking some cream on the skin and swiping it across the skin, there will be certain layers that travel at different velocities, where the one closest to the hand that's pushing it against the skin, that layer will be traveling more quicker than the layer of cream that is directly touching the stationary arm skin. Shear rate is the rate which layers move past each other. Viscosity is a measure of a fluid's resistance to flow. Blood flow will either be laminar or turbulent, and Reynolds number for a liquid flowing in a cylindrical fluid is a way we can predict those. So when it comes to blood flow, what we have is we have different layers, sort of like hollowed out rings, where we have our vessel central axis, where we have our direction of flow, and our hollowed out rings slowly decrease in radius as we get to a certain point. This would be the laminar flow that we have in blood vessels. And then we have a parabolic velocity profile of changing velocity per layer, where the layer is closer to the stationary phase or the vessel which is not moving. This layer will travel slower than the layer that is closest toward the center. Therefore, blood flow in the center vessel will have a higher velocity than that which is closest to the vessel. As far as laminar flow, that's where we have blood flow flowing rather linearly, and the velocity is consistently lower as we get closer to the walls and greater as we get closer to the central axis. Turbulent flow, whether we have some obstruction or some malformity in the tube, in the vessels, can cause all these velocity profiles to not be so linearly parabolic, but instead are crazily going all over the place in some non-predictable way. Calculating Reynolds number is a way of predicting whether we most likely definitely have laminar flow in the vessels, which for vessels would be a Reynolds number less than 2,000. And if we have a Reynolds number of greater than 3,000, then it's usually a high likelihood of being turbulent flow. The in-between period for other liquids is usually called the transient phase versus the laminar and turbulent, although for blood flow we usually think of things as just laminar or turbulent. Reynolds number, that can be calculated by RVP or RV rho divided by eta, where R is the vessel radius in meters, V is the average velocity in units of meters per second, or the average velocity of a cross-section of that vessel. Rho is the liquid density in units of kilograms per cubic meter, and eta is the viscosity in units of Newton seconds per square meter. Therefore, the units of our Reynolds number would effectively all cancel out, and we just have a unitless number. And just a prediction, again, for laminar, a Reynolds number that gets to less than 2,000 is usually due to turbulent flow, and if it's greater than 3,000, that's usually indicative of turbulent flow, where less than 2,000 would be laminar. The in-between, while usually not used for blood flow, could be called transient for other liquids. Now then, the reason why we got these units to cancel is because a Newton going from force equals mass times acceleration, a Newton is the same as a kilogram meter per second squared, which we can replace as an inverse Newton as second squared per kilogram meter, simplifying all of our remaining units from meters to the fourth times kilograms over second squared meters cubed. That gives us meters times kilograms times over second squared times inverse newtons, which would be second squared over kilograms meters, and thus we have some unitless parameter. Let's look at the law of continuity. This is only for laminar flow of an incompressible fluid flowing through rigid tubes. The volume flow rate Q must remain constant, no matter if that tube expands or compresses. The rate for a certain amount of volume to flow must remain constant. Typical units for volume flow rate include cubic meters per second, milliliters per second, liters per minute, some unit of volume per unit of time. Because, according to the law of continuity, the volume flow rate at some point in time, Q1, must be equal to the volume flow rate somewhere down the vessel, Q2. Therefore, this is some constant, and we can take that as Q equals the change in volume per time, change in time equals some constant. So if we increase the volume, we increase the time. If we decrease the volume, we decrease the time. These have to change in such a way that we still have some constant value always for Q. For example, if we multiplied the volume by 3, then we multiplied the time by 3. Now, another way of looking at Q is the combination of S times delta L over delta T, which is the surface area in square meters times the change in length of that volume, or times the linear length of that volume. We can think of it as the height of a cylinder, divided by the time it takes for that volume chunk to flow. And we can replace delta L over delta T with the unit of velocity, meters per second. Therefore, since our volume flow rate must be a constant, Q1 equals Q2, or S1V2 must equal S2, or S1V1 must equal S2V2. The surface area times the velocity at one point in time must equal the surface area times the fluid velocity at some other point in time. Therefore, if we would have the following system where we had some different transitions, whether we're going from, say, the arteries to capillaries to veins to another intermediate, that's what these separations are meant to say. We're transitioning from one part of the circulatory system to another. Let's say initially we're at some point in our vascular system where the surface area of the vessels is 2 centimeters square and the fluid velocity is 5 centimeters per second. What if you're asked, what is the surface area for the next boundary if the fluid velocity flowing through it is 1 centimeter per second? Well, S1V1 equals S2V2. Solving for S2, that gets us 2 square centimeters times the ratio of 5 centimeters per second over 1 centimeter per second, or 10 square centimeters. Now then, we have our surface area and fluid velocity at this point. What if we approach our next interface region, where the surface area is 1 centimeter? What would be the fluid velocity for that? Well, S2V2 would equal S3V3, because those are the two regions across our new separation medium or our transition medium. Fluid velocity E3 would just be V2 times the ratio of S2 over S3, or 1 centimeter per second times the ratio of 10 square centimeters per 1 square centimeter, which that just gets us to 10 centimeters per second. Now then, let's look at volume flow rate versus pressure. Here we have two curves, the top curve representing normal flow, blood flow in a vessel, and the bottom curve representing blood flow due to atherosclerotic stenosis, or narrowing of the vessel. What we have on our axes are pressure in response to volume flow rate. And what we see is, in order to get a higher volume flow rate, it requires a higher pressure. Now, for healthy blood vessels, in order to increase the volume flow rate a certain amount, it only requires a small change in pressure to do so. But if we have turbulent flow with some obstruction in the blood vessels, what we see is to get the same small change in volume flow rate, it would require a substantially larger change in pressure, or substantially more work from the heart, which is just a way of showing why having blockages in the heart can be so traumatic, because it takes greater pressure to achieve the same change than what would happen in a healthy heart. What we now have is the Hagen-Poiseuille law, The factors affecting the volume flow rate, Q, through a tube is what this law looks into. If our bodies ever need to change the volume flow rate in our vasculatory system, it can change the pressure difference at the ends of the tubes, at the ends of those interfaces of change. It can affect the fluid velocity, or if we wanted to, we could affect our fluid viscosity, eta, our tube radius, r, or our tube length, L. Because the volume flow rate, Q, is equal to pi r to the fourth divided by 8 eta L, all of that multiplied by our change in pressure, or P final minus P initial. This is similar to the electrical circuit we talked about when it came to standard resistor circuits. Essentially, the Hagen-Poiseuille law, we're going to look at what's called vascular resistance. Essentially, Q equals pi r to the fourth over 8 eta L times delta P. Our volume flow rate Q is similar to our current in our electrical system, and our change in pressure is similar or analogous to our change in voltage. Therefore, this term right here, pi r4 over 8 eta L, that's similar to the inverse of our resistor in our circuit. Therefore, if we take the reciprocal of this, vascular resistance in vessels is equal to 8 eta L over pi r to the fourth, or 8 times the viscosity times the linear length across, or the height of our cylinder, multiplied by pi times the radius to the fourth power. Another way of looking at it is the change in pressure between 2 points in the vessel, P final minus P initial, divided by the volume flow rate between them. And if we want to have a similar equation to I equals V over R, that would be Q equals delta P over vascular resistance, which shows up in physiology. Now, the units for vascular resistance, typically we'll see them as either a Pascal second per cubic meter or 1 millimeter of mercury per 1 milliliter per minute. Millimeter of mercury being the pressure unit, and minute per milliliter, but inverted, being our area, our volume, our time per volume. Some sample problems in calculating vascular resistance. The brain flow rate of 750 milliliters per minute with a pressure difference of 100 milliliters of mercury. Determine the cerebrovascular resistance, CVB. Well, no matter what region we're talking about, volume flow rate is equal to the change in pressure divided by the vascular resistance. Therefore, if we're given two of those quantities, the vascular resistance to flow in the cerebrovascular brain region, that would be our change in pressure over Q, or 100 milliliters of mercury, times 750 milliliters per minute, which gets us at 0.13 millimeters of mercury minute per milliliter. Let's say we're looking at the lungs, which can have a flow of 100 milliliters per second. The mean pulmonary arterial pressure is around 16 millimeters of mercury, and the mean left atrial pressure is 2 millimeters of mercury. The vascular resistance of the lungs would therefore be what? Well, let's first convert our flow units. We have 100 milliliters per second. We can times that by 60 seconds per minute to get 6,000 milliliters per minute. Now then, let's take the difference in our pressures, where we have, if we're looking at the resistance in the lungs, then we want to take the pressure that is at the lung minus the pressure at the left arterial point. That would be the difference of 16 minus 2 millimeters of mercury, and then we'll divide that by 6,000 milliliters per minute, which gets us a vascular resistance of the lungs of 0.0023 millimeters of mercury a minute per milliliter. Now then, let's look at parallel circuit blood flow vessels. This can be seen in the capillaries, the region between an artery and a vein, where blood vessels branch off in multiple areas to help fuel cells. If we want to look at our arterial volume flow rate QA, for parallel circuits, parallel vessels, that's just like having a parallel circuit when it came to current. We want to add up Q1 plus Q2 plus Q3 because the arterial current flow rate is going to partially break off into one path, the other, and then the final, and they're all going to come back together to equal the total volume flow pressure, which in this case is going to be equivalent to the volume flow rate through the veins. If we look at the change in pressure, that's sort of like voltage. The change in pressure between the pressure in the veins and the pressure in the arteries, well, that's going to be equal to the overall pressure across each total path, each parallel path, or the pressure in the veins minus the pressure in the arteries will equal the pressure across P1, the pressure across path 2, and the pressure across path 3. And one last bit, the equivalent resistance or the equivalent vascular resistance, because these are parallel paths, will be 1 over the vascular resistance in path 1 plus 1 over path 2 plus 1 over R3, all raised to the inverse power. And just adding that QV term just to emphasize the volume flow rate is remaining constant. So volume flow rate similar to current, pressure similar to voltage, and vascular resistance just like current circuit electrical resistance. Now let's look at a series circuit when it comes to blood vessels. Well, in this case, whether we're going from different points in a series, we're going to have some pressure drop across our first interphase region between one change phase, one medium of transfer to the next. And then in our next vessel segment, we'll have a second pressure drop, and then we'll have a third pressure drop across our third region. Each region will have their own resistance to flow as blood flow is trying to move through those blood vessels. And no matter what, we must have some constant flow rate Q. Due to being in series, the volume flow rate that's going through R1 is going to be the exact same value flowing through R2, such as what flows through R3. Because we're not in parallel paths, we're not losing some of that total volume flow rate. It's just remaining a constant going through each path. Therefore, the volume flow rate Q equals the pressure divided by the equivalent resistance, and that will equal the volume flow rate through Q1 equal to Q2 equal to Q3. The total pressure, since we're in series, is just going to be P1, the change in pressure 1 plus the change in pressure 2 plus the change in pressure 3. And to simplify that, that would just be the volume flow rate times R1 plus volume flow rate times R2 plus volume flow rate times vascular resistance 3. And if necessary, we can have our simplified vascular resistance equal to R1 plus R2 plus R3, just like any series resistors. The last law we'll talk about is the Bernoulli principle, and this is for non-viscous fluids only. This says that the total pressure is equal to the lateral static pressure plus the dynamic pressure, or PT will always be some combination of PL plus PD, and that will be a constant. Think of lateral pressure as the pressure that keeps the walls of a vessel open. It pushes out on the walls. It's perpendicular to the flow of blood. As we have a certain larger vessel, we're going to have a larger lateral pressure. And as we get into a more narrow vessel, we'll need a lower lateral pressure to keep those walls open. And then we'll have a larger lateral pressure keeping the cylinder, so the cross section of these vessel walls open. However, since the total pressure must be constant for non-viscous fluids flowing through these vessels, what this means is as the lateral pressure needs to either increase or decrease, the dynamic pressure will have to change as well. Therefore, when we have larger lateral pressure, we'll need less dynamic pressure pushing the blood through that vessel. And then as we need less lateral pressure, we will have greater dynamic pressure pushing the blood flow through the vessel. And then as we once again increase our lateral pressure keeping the walls open, we'll have a lower dynamic pressure pushing the blood through the vessels. And that is just what the Bernoulli principle is. So, for example, if we look at this sample problem in vessel 1 or region 1 of our vessels, our total pressure 1 must equal the total pressure in region 2 must equal the total pressure in region 3. That must always be some constant. Now, the PET1 is just the lateral pressure in 1 plus the dynamic pressure in 1. P total 2 is just the lateral pressure in 2 plus the dynamic pressure in 2. And then the total pressure in 3 is just its lateral and dynamic pressures added together. And those are going to all equal each other to be some constant. The formula for dynamic pressure is formally 1/2 the fluid density times the fluid velocity squared. So if you're ever given those parameters, you should be able to connect all these things together by the Bernoulli principle and the Hagen-Poiseuille principle, the law of continuity, and all of our other laws as well. That would be the cardiovascular system. Just to briefly get into the nervous system, because that is more akin, where the blood is similar to a resistor circuit, the nervous system is similar to an RC circuit with capacitors that keep charge separated and resistors that allow for ions to flow. Our capacitor in this case is going to be the cell membrane of our nerve cell, which is pretty good or very excellent at separating charge between the outside of the cell and the inside of the cell. Resistors can be ion channels that allows ions to flow from the outside of the cell to the inside or reverse. In this case, we're looking at axon channels, which allow flow either between the inside or outside of the axon to the inside of our axon. The components of our nerve cell is the dendrites, which are the shorter regions that we use to collect electrical signals from other nerve cells. We have our cell body, which is just like a normal cell. It has a nucleus, it has organelles, it has the ability to function like a cell. And then we have what's called this longer axon, which is the tube that's meant for propagating electrical signals to other nerve cells, passing them to other dendrites. The propagation of electrical signal is from dendrite to the cell body to the axon. And here we're going to look at some further information. What we have here is the axon that's meant to pass messages from one nerve cell to the dendrites of another. It will end in the terminal branches of the axon that forms junctions with other cells. Something that's particularly important about the axon is the myelin sheath covering the neurons. This helps decrease the capacitance, which leads to a substantially quicker electrical signal passing through the myelin sheath, or passing through the axon. Without the myelin sheath, the neural impulse would be substantially slower and not functional for what we need it to do. So, to end things off, when we look at the capacitance of a nerve cell, common ions are usually sodium ions, potassium ions, and calcium ions. One of the common anions would be chloride anions, where the positive ones are cations. Between the inside and the outside of our axon, our cells try to keep a difference of more positive on one side and more negative on the other side. And the phospholipid membrane is very effective at preventing charge from passing through, which is why the cell membrane would be our capacitor. It can be thought of, the cellular membrane can be thought of as an insulator, and the myelin sheaths are what acts as an outside barrier to outside of the axon. Therefore, all we care about is the charge difference between the inner and outer portion of the axon, and not the overall outside environment itself, whatever's outside the myelin sheath. This helps make it so that the axon can separate charge with a lower capacitance, and thus, because of the lower capacitance, is able to pass those neural impulses quicker down the axon to the next nerve cell's dendrites. Just one final explanation. Again, when we're comparing the circuitry to the nervous system, what we have is membranes acting as capacitors, and what we have is ion channels that may allow certain ions to pass through the cellular membrane. Those would be resistors. For biological systems, you would usually see those with measurements in conductance instead of resistance, which if you see that, just treat the equation like it's a resistor. But just know that anytime you see a resistor in our circuit equations, conductance is the inverse of resistance. So a conductor G is equal to 1 over our resistor R. And conductance would be units of Siemens, which are just inverse ohms, also called mhos. In any case, that would conclude our lecture on circuitry and physics, and briefly comparing them to the vascular system, circulatory system, and what we see in our nervous system. So just around the hour and 25-minute mark. Thank you all for participating in this lesson. Likes and subscribes are not needed, but they are appreciated and fun to see. And always, peace.